So my talk will be beyond the halocyan towards pathogen identification using PET-CT. I'm working in nuclear medicines. I'm a radiopharmacist preparing and developing compounds used for imaging purposes. Okay, that one. So I will shortly talk about fungal infection and diagnosis. It is not my core expertise, so I will keep that briefly, but explain to you a little bit about molecular imaging in PET, and then the attempt we did to image aspergillosis with what I'm going to explain. So the problems have been addressed very much in detail yesterday and with our previous speaker. So I mean, I don't have to repeat very much. Well, I want to stress that we are now using a lot of antifungal drugs that are related to high costs in healthcare systems, and using that, and that's what I learned during doing these projects, empirical therapy, partly prophylactic therapy, with all these drugs leading to high costs, but are also related to problems of toxicity and drug resistance development. And one reason is that the mortality related with invasive aspergillosis is still very high. Well, again, for someone coming outside of the field, this is really surprising to read that the mortality rates are that high. And partly, and that's what you read in all these reviews, that this is due to limitations in diagnosis. So we have heard a lot about the diagnostic possibilities in vitro, with all the problems related to specificity, but also particularly sensitivity. I will not repeat anything on that. And we have the possibility to trying to image in invasive fungal diseases, particularly aspergillosis. And we have here just radiography, but particular CT with the characteristic halocyans that again have a low specificity. That's one example on patients with an invasive aspergillosis, and you see here the typical sign that is this what is called halocyan, this that is indicative for aspergillosis, but is not specific, so can be related also to other underlying diseases such as inflammatory processes or other infections. So how could we make this more specific? And here I come to what the nuclear medicine side can provide, which is a technology. It is called positron emission tomography, or PET. That and you see here this system at our hospital, this PET-CT system that is based on the use of positron emitting radionuclides. These positron emitting radionuclides annihilate with electrons, giving you gamma rays in 180 degrees that can be detected simultaneously on these detectors. This results in a system that allows you to detect radionuclides more sensitively, but also gives you a higher resolution than has been established in clinical routine, in particular in oncology, over the last 15 years. So now every larger hospital has such a PET-CT system, and there is one just around the corner here. Combining this positron emission tomographer with a conventional computed tomography system. And the features of this system is that you can combine the anatomical information, mainly that you get from the CT, with the molecular information from a radio-labeled drug that gives you some specific information on molecular or functional processes, and you can combine these images and have the anatomical correlation by the CT, so you can exactly see where it is located, and you have a sensitive molecular information on some functional processes. So this is the idea, and we can use a number of radionuclides, particular for positron-emitting radionuclides. The main we use today is fluorine-18 with a half-life of 110 minutes, but also we have radiometals like zirconium-89, copper-64, or particular gallium-68 that has been introduced more recently and is more and more widely used for these molecular imaging applications, because it can be easily obtained with a very short half-life from a so-called radionuclide generator. So we have this available every day whenever we need it. But also it can be combined with specifically targeting molecules, such as for example here, a peptide targeting a certain receptor and giving us the signal of the receptor density, in this case an oncology patient, in very sensitively the correlation with the receptor density in the tissue that gives us then an indication of the pathology in this patient. So this is the concept of molecular imaging and using positron emission tomography in this context. Interestingly, for many years, colleagues have used chelating molecules such as Desferrioxamine B for chelating those radiometals stably to bind it to, for example, antibodies or peptide for molecular imaging purposes, including gallium or zirconium ions. This is an example of a zirconium-labeled antibody in a patient showing the uptake in tumor lesions by this zirconium bound via this actually siderophore. Okay, so I have some questions. I made some questions. So my first question is related to positron emission tomography, and where we use radio-labeled molecules in combination with positron-emitting radionuclides. And here is a list of radionuclides, and you can choose which one is the one that emits positrons that we can detect. So I have to... Oh, yeah. Oh, that's pretty good. So the majority has remembered gallium-68. Technetium-99m is a very widely used radionuclide, but it's not emitting positrons, but gamma rays as such. And carbon-14 we cannot image, but that's a good outcome of this. So let's continue. So for a long time, people in our field have tried to develop agents that could be used for imaging infections in general. So looking at targets that are accessible for that, and most applications, also part of them that we have today, are indirect methods. So trying to image indirect processes related to infection processes. For example, radio-labeled leukocytes are used widely, particularly in the US, for general infection imaging. Of course, it would be more interesting and more specific to have tools to imaging the pathogen itself, being it bacteria or fungi. And also here, people have tried to develop different compounds to be more specific in this respect. So today we are using, as I mentioned, labeled white blood cells, or also, for example, FDG, which is a glucose analogon that gives us information about increased glucose consumption in areas that is also related in infectious diseases. But a lot of papers you can find on radio-labeled antibiotics, or also antifungal agents or antimicrobial peptides. What has been used for a long time, interestingly, is gallium citrate as such, initially as gallium-67 for SPECT imaging, but now also as has been proposed in terms of PET imaging for infection imaging. And some papers have come out recently showing that there is some information that you could gain from this compound, which is at the end, again, an unspecific mechanism, because the gallium 68 that you inject transfers to transferrin, and you get some signal related to infectious sites, but they are pretty unspecific and have not really come into anywhere into clinical routine. And an example which is maybe a more specific attempt, again, SPECT and nothing to do with fungal infections, but people have labeled an antimicrobial peptide, UBI, with a radionuclide, and used this also in patient studies, and they have received some or presented some images that show some potential specificity of such an attempt to get a more specific imaging signal of infections in general. Again, this is not any specific for any particular bacteria or fungi. So when you look at such imaging agents, what we need that we get this radioactive signal into an infection is that we have, and this signal then will be specific, that we should have a specific interaction of our radiolabeled molecule with a pathogen. We then, what we know that it would be good to have a mechanism that actively accumulates the radioactive signal at the site of infection and keeps it there, so having a trapping process, and having a molecule that in general has favorable pharmacokinetics, including rapid elimination from healthy tissue. So I was visiting a PhD meeting several years ago and stumbled over a poster from Mr. Haas from our microbiology department, which dealt with iron and infection and with siderophores, and I was not really having an idea what has iron to do with infection. I mean, you know much better than me that iron is essential in the human body, but also plays an important role in infection processes. And there are people defining the infectious process also as a battle for the iron between the host and the pathogen. So on the one hand, the host has developed mechanism to withhold iron from the pathogen itself with a number of things like iron chelating molecules, but also siderocalins that bind siderophores that are emitted from bacteria or fungi. But also the pathogen is fighting for the iron, and in particular Aspergillus has been investigated very in depth by one group in Innsbruck by Mr. Haas, looking at the iron acquisition of Aspergillus. There are different mechanisms involved, but the main, and that is what has been shown, the main mechanism for acquiring iron by the pathogen is the siderophore iron uptake, which is a specific mechanism where the pathogen synthesizes iron chelating molecules. The Aspergillus fumigatus, particularly 3-acetylfusarenine C. It's a cyclic iron chelator that is excreted and then specifically binds the iron, which is then taken up by a dedicated transporter and intracellularly metabolized and transferred also to intracellular siderophores like ferricrocin that is shown here, and then iron stored in the vacuole. What surprised me is that this Aspergillus species can produce up to 10% of their biomass of siderophores. So this was very astonishing for me. Maybe it's not, you know that have learned that in your studies, but that was very impressive for us. So they have also shown the role of the siderophore system in infection in many studies. That's just one part of it, where they have shown that if you block the siderophore biosynthesis, that within the fungus, then the fungus becomes avirulent, and mice infected with this survive as compared to the wild type. If you modify it further down the line, where you only partly block siderophore synthesis, you again get a longer survival, but which is not so pronounced as blocking here. So very convincing data that this siderophore system is very important for the fungus, but it's also very important within the infection process and is upregulated during the infection. And when I come through the poster, we just had started with using gallium-68 in our hospital for labeling some molecules. And then I thought, well, the gallium has very similar properties to iron, to ferric iron. It virtually has the same ion radius, some chemical differences, in particular that it's not reducible as compared to iron, from iron 3 to iron 2. But in vivo, it behaves very similar to ferric ions. So the idea was, okay, you have these iron-binding siderophores, particularly this TAF-C, and that normally binds the iron, is excreted by the fungus also during the infection process. So can you not take this molecule and replace the iron by gallium and the gallium-68? So that was the idea, and thereby introducing a radioactive signal inside the fungus. Thereby having an active transport mechanism into the fungal infection. With the advantages in that you have gallium-68 with a very short half-life, you can use it for positron emission tomography that has a very high sensitivity and resolution, and you have a kind of peptide that we know has favorable pharmacokinetics. So what we did is we took some siderophores, we took TAF-C, but we also took FOXY, which is actually a bacterial siderophore, a non-cyclic one, and a ferrichrome and ferricrosin, and try to label that with gallium. You see here HPLC chromatograms that you take a very small amount of the siderophore and you can label it, and it labels very nicely and specifically. With the gallium, gives a very stable complex. And then what we did, we looked in vitro in Aspergillus cultures, and could nicely show that when the culture is done under normal conditions versus cultures in iron-deficient conditions. In iron-deficient conditions, the uptake of the siderophore is extremely upregulated, and we can block this uptake by sodium acid. So it's an energy-dependent mechanism, and it's quite specific as we can block it with the siderophores. What we also showed is that if we incubate that it remains in the fungus, so there is no release of the gallium, that it remains in the site of infection. This is another slide comparing different siderophores over time and the uptake, showing that not only in Aspergillus fumigatus TAF-C, but also ferricrosin, fusarenin C, or FOXY are taken up specifically, whereby TAF-C and FOXY showed the highest values. What is important for such an imaging tool is that it's also having reasonable pharmacokinetics, and that this is just biodistribution studies in mice, injecting the radio-labeled gallium-68 labeled TAF-C in mice, looking at 30 minutes, 90 minutes, and you see here the organ radioactivity in different organs, and you see particularly after 90 minutes there is almost no radioactivity in normal organs or blood, so it's rapidly washed out, and this is what we want, and what we also could show that it's stable in vivo. So it's not decomposed, it's not practically not metabolized. So very nice properties. We then went into our own PET camera system and looked into a rat pulmonary infection model with Aspergillus fumigatus. And with this normal camera, we could already show that, well, in normal rats, we did not get any signal, and in severe infections, we get a strong uptake of this radio-labeled compound. And these are the in vitro data that correlated with the severity of infection that we proved afterwards, taking out the lungs of these rats. So it's a pulmonary aspergillosis model. We then went into dedicated systems for animals, so micropet studies that are smaller systems with even higher sensitivity and resolution. And this is a dynamic imaging of this compound in in an infected rat, and you see that it's rapidly taken up, and you see a signal of radioactivity in the area of the lung that comes up rapidly and remains there, and here you see the washout of the kidneys, and that's 60 minutes after injection. Another example, we also used FOXy and here TAFC, some images of rats in these infection models, and you see in infected rats, you see a clear signal without no signal in the control animals. This you can also combine this with the CT, and this is a PET CT slices. That's the CT, that's the PET signal, and that's the overlay. And you see that these were pretty severely infected rats, where the CT was also pathogenic, and the radiolabeled signal was very much overlaid in this system. Well, that's my second MCQ question. So in these experiments, we could show that we could label this siderophore with gallium-68, and particular promising was the TAFC as a siderophore, and TAFC stands for one of these names. So maybe you remember which one it is. Very good, 43%. That's pretty good. Yes, 3-acetylfusarenine C. So that's an acetylated version of fusarenine C. That's also produced by Aspergillus fumigatus, and the main siderophore used by this fungus for iron acquisition, TAFC. Okay, so there are other issues related to that. One is the specificity of this system for fungal infection, and so we looked in vitro in different microorganisms, but also, for example, in lung cancer cells that we cultured. How is there a specific? Can we find a specific uptake of the radiolabeled siderophore? As it is known that even though many of these microorganisms cannot produce the siderophore, maybe, but they have uptake mechanisms that also non-siderophores they are not produced can be taken up. So the so-called xenosiderophores. That is known for some organisms. But so what we found for the TAFC, which is the one that's produced by Aspergillus fumigatus, labeled with gallium, that we have a very high specific uptake in fumigatus, but for example, practically no uptake in Aspergillus flavus or terreus. But we found some uptake in Fusarium and Rhizopus species, whereas the bacterial species did not show any uptake. This was in contrast to, okay, so if we combine fungi, so it was highly specific for fungal infection, and whereas yeasts, bacteria, or cancer cells did not show any uptake. I thought there was, okay, well, this was in contrast to the FOXy, which is a bacterial siderophore, where we also found a very high uptake in Staphylococcus species, interestingly. We also tried to image that in vivo, and this is imaging of the radiolabeled siderophore in an animal model with a sterile inflammation, because you also want to know is there any unspecific uptake, but also in a Staphylococcus infection. As you see here the FDG scan, which is the glucose metabolism that is increased in these areas of inflammation and infection, whereas in the really infectious area there is no signal at all of the radiolabeled siderophore, showing the specificity of this compound for this process. We also got to try to publish something, and the reviewer said, okay, this could be not the radio-labeled siderophore that you are looking at. It could only be the gallium-68, because the gallium-68 could be, let's say, transferred to a siderophore which is excreted by the microorganism. So are you sure that you have a specific signal related to the compound that you are using? So and these are images in normal mice of the citrate versus the TAF-C, and you see the citrate is transchelated to transferrin, and then you have a very long circulation time, so you have a high background signal. You see the lungs, you see liver, you see blood pool, whereas the TAF-C, and these are again PET-CT images, you see the kidneys and the bladder, which washed out very rapidly. And we did some more studies in infection models. It's just some images that you, at the end, to show you some PET-CT images, which are now, well, the software is getting more fancy with the CT images in white, and you see the radioactive signal in yellow. You see the kidney and the bladder as excretory organ, and you see the infectious side of in the lung in this red again. Or another way of showing that is showing here with a high resolution image of the lung, where the blue signal indicates specific uptake of the gallium-68 labeled TAF-C, which is not there in the control animal. That we also did other models. This is the mouse model that many of you may know, the intranasal model. And you see here the normal mouse, and this is the infected mouse, where you again see the pulmonary infection and the renal system and the bladder that has a lot of radioactivity due to the excretion of the compound. So the idea was to translate this into a clinical setting. The problem that we have with radiopharmaceuticals, radio-labeled molecules that we use for imaging, is that they are medicinal products. So we have to fulfill the requirements for related to GCP, GMP, doing toxicity studies, GLP, so it takes money at the end to do that. We tried to get some money in the last call, and we closely failed to get it, but we already did some work and have some ideas how to further translate this. One thing I want to show you is that we looked into the production of the TAF-C by a diploma student, and could show that, I mean, the Nidolans as a non-pathogenic strain has a high production rate of TAF-C and makes it pretty purely. That's the TAF-C peak, whereas fumigators, for example, also makes fusarinin C, that is this peak here, and makes it in quite large amounts. So in a 5-liter culture, we can make 200 milligrams of this. We can isolate 200 milligrams of this TAF-C, which is enough, to give you an idea, 200 milligrams to study 20,000 patients with this compound. So we need about 10 micrograms of the compound to radio label it with gallium and to be injected. So that's called microdosing. But we are not the only ones looking into imaging possibilities that are potentially more specific. There are a number of papers using, for example, a peptide specific for Aspergillus fumigatus. There is a paper that was radio-labeled for imaging purposes. I just want to show you one recent development with antibodies, with a radio-labeled antibody. There is a group, it's called Matthias. They have a FP7 grant for developing a radio-labeled to radio-label an Aspergillus-specific antibody. What they did is they labeled it with copper-64, which is also a PET radionuclide with a half-life of 12 hours. And they recently published this paper in PNAS and where they, for example, could show that they are, with this radio-labeled antibody, pretty specific. Again, in the pulmonary aspergillosis model, in the rat, they used a combination of PET and MR for imaging. That's an even more expensive system to use. But you see here the control, you see bacterial infection, and here the fumigatus, and only the Aspergillus fumigatus infection shows an uptake of this radio-labeled antibody. The advantage maybe if this is that it's more specific, so really Aspergillus fumigatus specific. The disadvantage, in my opinion, is that it's a radiolabeled antibody, and we know that antibodies as larger molecules, you need longer imaging times. So typically you get the signal after 24 hours or something like that, which makes the method as such a little bit practically, I think, challenging. So with this, I end my talk, which is not so far into the clinic as the previous talks. But what we did in the last years, we looked into the siderophore system to use especially gallium-68 for detecting fungal diseases. And in particular, the TAF-C has shown to be a very good compound for this, and we are looking into translating that into a clinical imaging setting. And this work was all a collaboration with different institutions. Some of you know the group of Mr. Haas in Innsbruck, but also Ms. Lasfleurl has been very much involved in that, and people who did the imaging studies for us, and the consortium that we had for this last call. With that, I thank you for your attention.